Are you looking to create your own Eurorack modules but find some of the electronics concepts intimidating? This video series may be just for you. In it, I'll cover a module that has some of the most basic electronics you'll find, the mixer. I'm Brian from EurorackDIY, and I'm here to share with you how I make inexpensive Eurorack modules that sound and look great. Welcome back to my series on creating a simple mixer module. In my last video, I demonstrated how an op-amp can be used to add two voltages together. There's a link to that video below if you'd like to review it. The example I was showing left off adding two 9-volt inputs together, but what it also showed is that you're limited as to the magnitude of voltages that you can add. They can never add up to more than the supply voltages of the op-amp. As more audio inputs are added together, the chances that they will add up to more than the supply voltage, either negative or positive, increase. Also, with a mixer, we expect to be able to adjust the ratio of the input signals that are being mixed together. What we need is a way to control the magnitude of the input signals, and we'll do that with the potentiometer. But first, we'll take on a little more of the math behind how the potentiometer provides this kind of control, specifically how two resistors in series can divide a voltage by a specific ratio. We say two resistors are in series when they're connected together one after the other, sort of end to end like this. And we also know in this case that the same current flows through both of them, and we basically know that by Kirchhoff's current law that we've talked about in earlier videos, where the sum of the currents into a node must equal zero, meaning the same current going into the node comes out. So at this point where the two resistors are connected, we know it has to be the same current, which means the same current flows throughout the whole circuit. Another property to know out of this is that two resistors connected in series, the resistance adds together to provide an overall current circuit resistance. In this case, it would be 2K ohms, where we have a 1K ohm resistor and a 1K ohm resistor together. We have the equivalent schematic sort of circuit drawn here. Now, using this property, we can calculate the current through the whole circuit, knowing that we have 9 volts dropped across both of these resistors. And using the portion of ohms, the current calculation from Ohm's law, where current is equal to voltage times resistance, we know that it's 9 volts across them, divided by the sum of these two resistors, which will be 2,000 ohms, which gives us 0.0045 if we were to divide that out, amperes, or in the case of making it simpler, milliamps in this particular circuit. Now, we also know then, so this is 4.5 milliamps, so we also know that we can also calculate now the voltage dropped across this particular resistor here, because we know that it's 4.5 milliamps going through this 1K ohm resistor. And using the form of Ohm's law, where we know that voltage is the current times the resistance, we get 4.5 milliamps, or 0.0045, times the 1,000 ohm resistor, which will give us 4.5 volts across this particular resistor here. And this sort of makes sense because we can see in this case the two resistors, if we know that it's going to be dividing the voltage, with them being equal, it should divide the voltage exactly in half. And so there's 4.5 volts from the negative terminal here. We'd also know that the same we have to account for the other 4.5 volts in the circuit, and that would be dropped across this resistor here. It'd be from the 9 volts to 4.5 volts. So we know that there's 4.5 volts dropped across here. One other thing that we can do is if we relabel these resistors, say like R1 and R2, we think about the total voltage as like, say, the voltage in, and we want to know this voltage here, we can call that voltage out. Then we can generate a general equation for this. And basically, again, the way we do that is we know the total current going through the circuit using a sort of a formula similar to this. And if we call this, right, V in, the total voltage there, it's going to be equal to V in divided by R1 plus R2 And then, so that gives us the current. And so now if we want to know the voltage across this particular resistor here, we'll call it V out. Using this same kind of equation here, it'll be I total, which we know is V in, R1 plus R2 times R2. And thus, simplifying that a little bit, I guess we'll get V in times R2 over R1 plus R2. And then we can go ahead and use the same general formula to solve for the current that we have here, and just prove to ourselves a little bit about how this voltage divider, this actually divides things and stuff. So in this particular case, we would have 9 volts, or V in, divided by R2, 1K, over R1 plus R2, which is 2K. This is our V out. And then we know that this is basically the K ohms cancel on there, which would be 9 times 1/2, which is equals to 4.5 volts again. So once again in this video, I'll be using Falstad's CircuitJS online circuit simulating tool to demonstrate some of these concepts. I'll leave a link to it below. I'll also leave a link to all of these circuits below. And so for our voltage divider, what I've gone ahead here and done is I've set up a 9-volt battery source and put an output to show us, like, in between there what the voltage is between them. So all I have to do here is draw in the resistors. I type the R key to get it into resistor drawing mode, and I can click and drag to draw a resistor. Conveniently, the default resistor is 1K. That's what we've been using in our example. So if we have two 1K resistors, we see that we do get 4.5 volts out of our voltage divider from the negative terminal of the battery to the midpoint of the two resistors. We can also demonstrate how the voltage divider changes as you change the resistance of the two resistors. So for instance, if we increase the top resistor in the circuit, we see that now this is dividing the voltage by 3 volts, or by 3 to 3 volts from the 9 volts. And then we can also show that the voltage divider exactly divides things in half if we use two resistors that are of the same value. So in this case, two 2K ohm resistors. It's also pretty straightforward to set up our voltage divider on our breadboard. And what I've gone ahead here and done is I'm using a 9-volt battery again for our supply, so it matches the other examples we've looked at. I have two 1K ohm resistors hooked up so that they're both plugged into the same row here, and then one of them is connected to the positive side of the 9 volts, and the other one is to the negative side, or as we're considering it, 0 volts. So we can, first of all, go ahead and look and verify the voltage out of the battery. It's slightly more than 9 volts, 9.5 volts, so we would also expect that our voltage divider won't be exactly 4.5 volts. And sure enough, if we plug this lead of the multimeter into the common point between the two resistors, we see that 9.5 volts has been divided almost exactly in half, or to 4.7 volts. So how does a voltage divider circuit apply to a variable resistor, also commonly known as a potentiometer? If we look at how the potentiometer is constructed, we'll get a clue. A potentiometer has 3 terminals, and the ones we'll use has a shaft that turns about 3/4 of a rotation from minimum to maximum. They'll also have a resistance specified, and this resistance is the fixed resistance between the first and the third terminals. The center terminal is the output of a contact that moves from one end of the resistor to the other, thus dividing the resistor into 2 parts. This contact is sometimes referred to as a wiper. I'll typically use this style of potentiometer in breadboards, and then when I make my modules, I'll use this one that can fit into a circuit board vertically and fits nicely in the sandwich between the printed circuit board and the faceplate of the module. The resistive material between the two outer contacts can be distributed evenly throughout the range of the potentiometer, thus giving a linear change in resistance. This will also be specified in the value of the potentiometer by the letter B. And we also have the value of the potentiometer, the 100K ohms. Both of these are examples of that. There are other distributions specified with other letters. Perhaps the other of most interest in the synthesizer world is the A or audio distribution. We won't be using that for our circuit, but they're often used to give the volume control a profile that matches human hearing, where the perception of loudness isn't necessarily linear. The symbol for a potentiometer is either like this for the US version of it, or the international version is like this. You can see that it mimics a fixed resistor in the body of it, but also has the third central terminal, and then it shows how that third terminal divides the resistance into two parts. This also sort of gives us a hint as to how it will operate as a voltage divider, as this looks a little bit like the voltage divider circuit, where we are measuring the voltage at some point in the middle of the range of the resistor. Setting a 100K ohm potentiometer to its middle position would thus create a voltage divider with two 50K resistors in it and have the voltage like we saw in our example earlier. Setting it to more around like a quarter of the way through the travel would make the resistor more like 25K and 75K and divide an input voltage by 4, or effectively multiply it by a quarter. So again, Circuit.js provides us with the ability to simulate potentiometers. The way that we get one is if we right-click on the background, go to Passive Components, and down to Add a Potentiometer. We're going to go ahead and draw it from the negative terminal to the 9-volt terminal in the circuit I've set up here. And after that, go ahead and set the value to the same 100K ohm resistance, although it will operate the same no matter what resistance it is. We just want to show it in our circuit the same way that we have been showing the examples. So now we have it set midpoint between the 250K ohms levels. If we want to change the resistance, we can come over to the right side of the screen, and we are now given a slider that will move the potentiometer just as it would a circuit, or in our circuits. And the other thing we might want to do is have an output so we can actually see the voltage for it. And so if we add analog output, click on the circle and drag, it puts an output here, and then we can, for that, have it show the voltage. So now that we have it 50K ohms above and below, we see that the voltage is exactly halved. And as we move the slider to the left, it moves the wiper downwards, providing less resistance in the bottom portion of the circuit, which thus then lowers the voltage. And likewise, if we slide it up, we'll get a higher voltage out of the voltage divider. Of course, we can also use the breadboard or look at the potentiometers with our multimeter to show how they operate. Of course, we can also go ahead and breadboard up these same example circuits, or go ahead and use the multimeter to measure the characteristics of our potentiometers. In this particular case, I've gone ahead and hooked up a 100K ohm potentiometer, first of all, between the two terminals of the fixed resistance. We can see it's slightly less than 100K ohms. This is on the 200K setting for reading resistances. And if we go ahead and connect this to the center connector, the wiper, we can see now with it fully in the left-hand position that it's at 0 ohms, and as we start to turn it up, it goes to 14K, 21K, 32K, the point where it's about halfway, set about halfway, 56K, and on up all the way to full scale, and we get essentially the same 97K, almost 100K ohms out when it's all the way at full scale. Now to go ahead and look at it in a circuit as a voltage divider, one of the things that I want to mention here is, and I'll leave a link below, is I found this great 3D print on Thingiverse. It builds a really nice carriage to put the potentiometer in this style of potentiometer in, so that it doesn't wobble back and forth on a breadboard like this. So like I said, I'll leave a link for that below. I've gone ahead and created a circuit where I've got 9 volts on this side, got the ground on this side. I've hooked, I've stuck a wire in so that it will connect the 9 volts to this side of the potentiometer and then ground to the other side. Let's go ahead and set our multimeter on volts on the 20 volt scale. And if we go ahead and plug this in, I've also got this lead here, which will be on the center pin. So when I hook everything up, so go ahead and plug this in that way, connect the ground side to the negative terminal of the battery, and then go ahead and hook this up in the circuit. It's a little hard to see, but it's over to the left now, and the potentiometer is a little over to the left, all the way over to the left. And if I go ahead and start turning it up, we can see that the voltage also starts to increase as the voltage divider goes through. And of course, at about halfway, we're also at about half the voltage, the total voltage, 4.6 volts of the battery. And then we can also just go ahead and turn this all the rest of the way up and see the 9.5 volts, full 9.5 volts of the battery. Earlier we looked at how 2 resistors in series behave in a circuit, and when they're connected like this, they act as a voltage divider. But the other way that resistors can be evaluated in a circuit is when they're connected in parallel. And in our mixer circuit, we actually will have parallel resistances, but we're going to choose values such that they won't be affecting the overall characteristics of the circuit that much. It's just that we want to understand that this can be an issue. We actually saw parallel resistances back in the first video in this series when we were looking at Kirchhoff's current law, and we had the 2 resistors connected to the battery, both to the plus and minus terminals. In this, what we saw is that the overall current through the circuit increased because it was the current between each of these 2 resistors. If we go back to Ohm's law and think about this a little bit, specifically the form that solves for resistance, which shows that the effective resistance of a circuit is the voltage divided by the current, because we saw that the current will increase in the circuit, we can reason that the overall resistance of the circuit has decreased by having the 2 resistors in parallel. I won't be going too much more into the actual math behind this, as I won't be calculating any of it in this series, but we'll see here in a bit where it affects the circuit. Now we can add potentiometers to the inputs of our summing amplifier circuits we developed in the last video. As a reminder, this is our summing inverting op amp that we had before, with 2 inputs going through 2 100k ohm resistors. To use the potentiometer as a volume control for our inputs, we'll add one for each of the 2 input signals, and we'll configure it as a voltage divider, meaning that we'll have the input at one end of the resistance, and the other end will be grounded with the wiper connected to the 100k ohm input resistor. This gives us the ability to select a voltage here that will control the amount of voltage going into the circuit, and the rest of the analysis then remains the same in terms of how it will add these 2 inputs together as they're scaled up and down. So for this, I'm using 100k ohm potentiometers for a few reasons. One is that we want to maintain an input impedance to the circuit which is fairly high, which means that the amount of resistance between this point and ground stays fairly high, and 100k ohms would be considered fairly high input impedance. Another reason is that there's an interaction between the summing input resistor and the potentiometer, between this resistor here and the potentiometer, as they effectively look like 2 resistors in parallel. If you remember, this point here, the inverting input will be kept at the same voltage as this one, and so as the non-inverting input, which is at ground. And so this is essentially, this end of this resistor is essentially grounded, and so now the lower portion of the potentiometer looks like it's in parallel with the input resistance. And then finally, we're going to be adding a capacitor to the input in a bit to block any DC offset, and we'll add it before this input portion here. And in this configuration, that capacitor is going to act as a high-pass filter, or it'll block the DC offset of the input signal. And because of the math behind how filters work and everything, we want to have a cutoff frequency, or the frequency at which the circuit is affected, below the audio range. And having a bigger resistor here makes it so that we can have a smaller capacitor, and the resistors, regardless of how much resistance they have, are all the same size in the circuit, but larger capacitors can be more expensive and end up being larger components in our circuit. So back to Circuit.js again, we can go ahead and show the same thing in the circuit. In this case, I'm going to show you what I did before. I know in the last video I didn't show how to actually add an op amp here. It's fairly easy. It's the same way as most of the other components. It is under active building blocks, and you can add an op amp either ideal with minus on top or the plus on top. In our case, we want the minus on top. We're going to go ahead and draw it into the circuit in this place that I've left blank for it. And so now we have the exact same circuit that we were looking at on the overhead view in the paper. And again, we can see how changing the resistance or the position of the potentiometer both decreases and increases the voltage at the output of the op amp. And then, of course, this is an inverting circuit, so it's the same. It's the magnitude of the input, but inverted, so minus 1.8 volts. Now we can return to the breadboard circuit from the last video where we had the inverting summing op amp set up. I have two inputs here. I'm going to go ahead and pull this one out since it'll be a little confusing to go ahead and have all that for the voltage, but to demonstrate the potentiometer's control of the input, we don't really need the two inputs. I'm going to go ahead and stick the potentiometer here. As you can see, I've got this pin ready to go to ground. This one here will now be connected to the 1K ohm or the 100K ohm resistor as the input to the circuit. And then what we need to do is put our signal on this pin here. So our signal again is going to be simulated by this battery. Go ahead and connect its negative input to the ground rail, and the positive input again goes to where we're going to have that potentiometer in our circuit. Also go ahead and hook up our voltmeter to ground and also to the output, so we can see without the potentiometer in there we have no voltage. I'll go ahead and set it over here to the left to start with, which will essentially have 0 volts across the voltage divider portion of it. And so when we plug it in, as we can see, actually 0 volts. So now as we start to turn the potentiometer up, we can see that we start getting our inverted voltage, but at the magnitude of the voltage divider as we continue to turn it up. And this will continue essentially all the way till we turn it to the right, and it is replicating the 9 volts of input voltage, but inverting it in the process. For my mixer, I also want to have a master volume control, meaning another potentiometer that can raise and lower the amplitude of all the input signals at once. I'll be using a TL072 op amp, and it has 2 amplifier circuits in it. So one way I might accomplish this would be to use that second op amp circuit as a single input inverting amplifier and have the potentiometer in the same place as we've done with our inputs. But I'm not going to do that. While this would have the effect I want, the one potential drawback is that maybe for some reason the sum of the inputs in the previous stage end up being greater than the supply voltage of the op amp. This would result in clipping in that stage or a loss of some of the signal fidelity. It turns out there's a way I can add the output volume control such that we can avoid this. We can do that by making the feedback resistor for the input stage into a variable resistance. So let's take a look at how that works. Remembering that the center terminal of the potentiometer divides the overall resistance in 2, we can elect to use only one of those 2 effective resistors as the resistance for the feedback portion of our summing op amp. We'll do this by connecting the center terminal of the potentiometer to the output of the op amp, and thus we'll only be using this portion of the resistor here as we move the wiper from one end of it to the other, changing the resistance of the feedback from 0 ohms or near 0 ohms when the wiper will be at this end to nearly 100K ohms where the entire resistor is in the circuit when it's at this end. You'll also notice that we connected this third terminal, it would be the rightmost terminal of the potentiometer, to the wiper terminal and the output of the op-amp. What this has effectively done is shorted out this resistance. I'm not sure that that's absolutely necessary in this particular circuit. However, it's usually a good idea not to leave any pins from any of our components just sort of sitting out there and floating. We're going to be using a 100k ohm potentiometer here too. It makes sense that when this potentiometer is turned all the way to the right, it's the same circuit as what we had when we had the 100k ohm resistor, a fixed 100k ohm resistor, as our feedback resistor. But what happens when we turn it all the way to the left, or possibly somewhere in between? In that case, we can go back to the analysis we did in the last video showing how the output voltage varied based on the currents generated in the circuit. So to look at this, we'll assume that the case where the potentiometer is turned all the way to the left, and so it's nearly 0 volts. We'll go ahead and draw back in this portion of the circuit with an input voltage. In this case, let's go ahead and use 5 volts and a 100k ohm resistor here. In that case, what we saw before is that we have about 5 microamps flowing into the circuit here. We know that this portion of the circuit has 0 microamps because of the characteristics of an op-amp. And so what needs to happen is this branch of the circuit will need to also satisfy that 5 microamps current need, but it will be doing so across a resistor of 0 ohms in this particular case. And to be able to do that, the output here needs to match whatever voltage needs to happen, but it's going to be near 0. We can go back and look at Ohm's law, where we're going to be solving for what voltage is necessary. In this particular case, the voltage is equal to the resistance times the current, or for our circuit, we'll have 5 microamps of current and we have 0 ohms of resistance. And so in this particular case, we can see now that a voltage of 0 volts is capable of providing that 5 microamps, even though it seems a little bit odd. And as you start to increase it slightly, there will start to be a slight resistance, and it will start to make more sense that the voltage will start increasing slightly until it gets to the point where it's the full resistor in the circuit when it's fully to the right, and it's 100k ohms again, and now it's once again having to have negative 5 volts on the output to be able to match that. Likewise in Circuit.js, this is how the master volume control works. We've gone ahead, put our 100k ohm potentiometer in the circuit. We have hooked the wiper up to the output of the op-amp, and also gone ahead and hooked up the extra pin, but as you can see, that it shorts out this portion. And again, we have minus 4.5 volts out. I've just gone ahead with a fixed input in this particular case, but you can now, moving the resistance, we can demonstrate how moving the wiper all the way to the left, basically making it so there is very little resistance in the feedback circuit. It reduces the output of the inverting op-amp almost to 0. And again, moving it to the right and almost all the way up to full scale, it's now in the inverted nearly minus 9 volts. And then finally, to show on our breadboard how we can use the potentiometer as the master volume control. Again, what we said is we're going to replace out the feedback resistance with a potentiometer for doing that. This is our feedback resistor here, so I'm going to go ahead and pull that out of the circuit. And then I have some jumpers here to go ahead and hook one side of the feedback resistor here, or where the feedback resistor was connected in the op-amp, to that. And we go ahead and put this here so we can see how things will line up. And then the other side of where that was connected to the middle connector of the potentiometer, or the wiper. As I mentioned, it's just a good idea to go ahead and tie that wiper and on the side that's on the output, which this is the output, to go ahead and tie those two pins together. So now with this, we can go ahead and plug it into those same pins, and with it there, we now have our full feedback. And we'll go ahead and we'll use the battery again as our input source. Again, hooking it up to ground, and then our input connect right here. In this particular case, and I probably wire this a little differently in the circuit, I've got the wiper all the way over to the right. So, and this is where it's actually seeing 0 volts in the circuit. So as I turn the knob more to the left, we can see that it's introducing more feedback resistance in the circuit. And again, at about halfway, it's about half the magnitude inverted again of the signal, and then continuing to turn it until the point where it's providing almost 100K again, and it's almost the full -9 volts. At this point, we've essentially built out and analyzed the core functionality of our mixer. There's a couple of other things we'll want to do to make our module more robust, and in the next video in this series, I'll take a look at those things. Plus, we'll do a bit of breadboarding of our mixer with actual audio signals. If you're interested in continuing to get this kind of content, please consider subscribing to my channel. Also, if you have any questions or things you'd like to see in the future, please leave a comment, and I love hearing about the DIY projects everyone out there is working on themselves. Finally, I'm also on Instagram at EurorackDIY, so drop by there too.